Hello everyone and welcome to the Extreme HPLC Technology Forum organised by the Analytical Scientist and supported by Paul, Phenomenex, Silcotech and Vici Valco Instruments. My name is Rich Whitworth, Content Director at the Analytical Scientist, and I'm delighted to host today's event, which features 4 experts, all poised to help you push your HPLC analyses to the extreme. Some housekeeping first. Please remember you can submit your questions for the live Q&A at the end of the presentations at any time. Just click the Ask a Question button. There's plenty of insight to be gained. You may have something application specific or perhaps a broader question about the limits of HPLC. On that note, if your question is for one of the speakers in particular, please let us know by adding their name at the start of the question. Okay, before we begin properly, I'll just offer a quick reminder of the agenda. First, we have Craig Tamble, who's an application scientist at Pol. He promises to improve the accuracy of your HPLC analyses while, thankfully, extending the life of your column. Next, we have Brian Rivera, a senior product manager in biologics at Phenomenex, who introduces us to pore control technology, which he says will help you improve SEC method robustness and transferability for routine aggregate analysis of monoclonal antibodies. Third up, we have Jesse Bischoff, who's an R&D scientist at Silcotech Corporation. He questions the very nature of high performance when it comes to some commonly used HPLC materials by delving into the dangers of metal ion leaching. Last but by no means least, we have Jennifer Copeland, who's an LC product manager at Vici Valco Instruments, who cuts us all down to size with a dedicated UHPL system for single cell analysis and below. Well, I think that's enough from me. I'll get this Extreme HPLC show properly on the road by handing over to Craig Tamble. Craig, over to you.
Thanks for the introduction. My name is Craig Tamble. I am a senior technical application scientist at Pol Laboratory. I'll be talking today about why proper filtration of analytical samples and mobile phases used in instrumentation helps in the generation of better, more consistent data and can keep your lab running smoother. I've been at Pol for 4 years in our laboratory group, supporting our broad customer base on a variety of lab filtration needs. I focus mostly on Pol's cellular, analytical, and tangential flow filtration product lines. And as the title suggests, today I'll be focusing on Pol's analytical portfolio. Let's start off by talking about analytical sample preparation and why it's such a big deal. Typically, analytical samples are in smaller volumes, from hundreds of microliters to a handful of milliliters. These samples get injected into very sensitive and expensive machinery with expensive components that, should they get blocked or gunked up with insoluble material, can cause issues from poor data quality all the way to damaging the instrument themselves, which can result in repeating experiments, instrument downtime, and increased expenditures to get instruments up and running again. That's why it's so important to make sure you're not only filtering your sample, but also using a filter that you can trust to perform properly day in and day out. Other solutions, buffers, or solvents are also run through these instruments, and those too need to be properly filtered to keep baseline steady and to keep consistency between runs. Failure to properly filter these can also result in contamination of microbes, which themselves can release biomolecules that will get read by certain instruments, making data interpretation difficult or impossible in some cases. Things that need to be considered when choosing the right filter for these steps are flow rates, or how long will it take to filter a sample. There's also retention ability, or will this capture microbes or other particulate matter consistently over a certain size. Often the better performing filters will come at a more premium price, but spending a little more to filter a sample can save you time and money in the long run by keeping instruments running better for longer periods of time with less upkeep. I'm going to start out talking on the sample prep side of things. As analytical technologies continue to improve, their sensitivities increase while sample volumes decrease. This means that the total amount of analyte needed for a run keeps decreasing, making the need for clean filtration more important as the ability to pick up on extractables that can be released from filters also increases. This also means you don't want to use filters that could potentially bind the analytes. That's where Pol's Acrodis syringe filters come in. We have a variety of membrane materials in our syringe filters, which you can tailor to your specific sample needs, or you can just opt for our universal Acrodis syringe filter with water-wettable PTFE membrane, which gives the broad chemical compatibility and cleanliness of PTFE, while also being able to be used with both hydrophilic and hydrophobic solutions, rather than just hydrophobic solutions like traditional PTFE. Here is a flow chart for all the different choices that need to be taken into consideration when making decisions on what filter the membrane material you will use. The first choice is what type of analysis is being done. A few choices are shown here, including general high performance or ultra high performance liquid chromatography tied to mass spec analysis, or maybe even more specific types of liquid chromatography using ion chromatography. Each of these will have different needs for pore size and membrane material. For standard HPLC, 0.45 micron filters are good to use due to the size of the packing material generally used for HPLC, where smaller particles less than 450 nanometers can make their way through the column and not cause any blocking. But as you get into UHPLC, the columns used for that use smaller material and have a tighter packing size that require 0.2 micron filtration in order to not block the columns with insoluble material. Then comes certain compatibility issues. For example, with LCMS, you want to make sure you're not introducing extraneous compounds that could potentially hide your analyte. This is where water-wettable PTFE comes in handy, as it's typically very clean and consistent from lot to lot. With ion chromatography, you're not wanting to introduce extra ions, so we have a specific filter with a washed polyether sulfone membrane to get many standard ion concentrations low enough to run your tests properly. For prefiltration, Paul has either straight glass fiber filters, which retain particulates larger than 1 micron, and we also have filters that contain a similar glass fiber filter upstream of the final membrane for use as a prefilter. This helps with throughput issues and also cuts down on the needs to spin down samples with a lot of debris, decreasing handling times and speeding up the sample prep process. There's the automation aspect to consider as well. Paul has a line of Acrodis PSF syringe filters that are compatible with most automated sampling equipment. And I'll talk a bit more on those shortly, so I won't go in depth into the hows and whys to that now. Finally, there's the volume of sample and the number of samples to take into consideration. Paul has lines of plate filters with different membrane material that you can filter multiple samples at once into receiver plates using either a vacuum manifold or a centrifuge, allowing for high throughput sample preparation. We have spin devices to handle low volumes for more low throughput applications. Then there are small syringe filters with 13 millimeter diameters for sample volumes less than 10 mils, and our standard 25 millimeter syringe filters for volumes up to 125 mils. One important thing to remember when using a syringe filter is to try and only use 10 mil syringes or larger, even if you have 1 or 2 mils of sample. With the 1 mil syringe, you can exert well over 100 psi of force on the membrane with just pushing down on the syringe plunger with your thumb. And this can damage the membrane and result in the sample passing right through the syringe filter without being filtered. This is also true with 3 and 5 mil syringes. It's not until you get to the 10 mil size and above where you really have to try hard to exert the pressure that can damage a membrane. Here we did a simple experiment to show the importance of filtering samples prior to running them in a standard HPLC system. Plugging and blockages are the main cause for column failure when doing an HPLC run. The main source of these blockages being particulate matter in a sample that can't get flushed out of a column and ends up stuck within the packed material. This decreases flow rates, which means higher pressures are used to get the flow rates needed, which can cause issues with peak separation and background noise. Eventually, the pressures get too high, and there's a complete failure of the column and system. And as you can see, this can happen quite quickly. The experiment here was filtering a latex bead solution with 0.45 micron beads that were either injected directly onto the column or filtered first with a glass fiber over 0.45 micron water-wettable PTFE Acrodis 1 filter. As you can see, less than 20 injections was all it took to spike the pressure to failure when the sample was directly injected. When filtered with a Paul Acrodis 1 syringe filter, over 1,000 runs were performed with no increase in column back pressure at all. If we run the same test with a competitor's 0.45 micron filter, column back pressure reaches the failure limit after around 500 injections. This goes to show that all 0.45 micron syringe filters aren't the same, and that getting the product with the best performance is important for keeping instruments running optimally. Let's dig in a bit deeper on the Paul Acrodis 1 filter with water wettable PTFE that was used in the previous slide. As shown in the example, it extended column life up to 52 times over not filtering a sample, and 2 times more than filtering with a competitor's device. Since we actually stopped testing the Acrodis 1 filter after 1,000 injections due to not seeing any back pressure increase, that is a vast underestimate of both those numbers, but the main takeaway is that proper sample filtration can indefinitely extend the life of a column, decreasing upkeep costs of an instrument and decreasing the cost per sample run. The water wettable PTFE membrane used in the Acrodis 1 is HPLC certified for low extractables, reducing unwanted peaks in HPLC traces and helping reduce baseline drifting, keeping run-to-run and lot-to-lot variations to a minimum. There are glass pre-filter versions which help in the processing of particulate-laden samples as well, and we have 0.2 and 0.45 micron versions depending upon what type of HPLC runs you're running. The way these filters are sealed helps to increase overall filtration area versus standard syringe filters, which is another way that Paul increases flow rates and throughput of our syringe filters. They're automation certified, come in a variety of different pack sizes, and the same Acrodis 1 housing comes with different types of membranes, which may be needed for different types of applications. If we look even further into the makeup of the Acrodis 1 with glass prefiltration membrane, you see that the glass portion is actually multi-layered, with pore sizes ranging from 40 microns down to 1 micron. This does a better job of trapping different size particles and increases throughput and flow rates of samples compared to more traditional single-layer glass prefilters. This increase is even greater when compared to filters with no prefilter at all. This filter family is also heat sealed rather than pressure sealed, which creates a better overall seal at the edges, helping to prevent particulate breakthrough around those edges and allows for use under higher pressures. It's this heat sealing that allows for a greater filtration area over the more traditional 3-piece ring molded syringe filters, where a bulky ring is cast around the inlet and outlet of a syringe filter to pressure hold the two parts together. The fact that the Acrodis 1 is heat sealed rather than pressure sealed allows for better profile geometry of the device over other syringe filters. It also gives the housing more strength and doesn't allow for deformation during robotic instrumentation handling, which makes for more consistent contact with inlet and outlet ports of the instrument. This strength also allows for more consistent overall size of the syringe filter, both for the diameter of the inlet and outlet and also for the total height. Again, giving more consistent contact within automated environments. Finally, the manufacturing and assembly of the Acrodis 1 2-piece syringe filter results in more rigid and consistent inlet and outlet sizing, making it easier to slip on and off in automation equipment, reducing failures during runs, increasing runtime lengths, and increasing overall throughput of sample testing. The rounded edges help to guide automated equipment into the proper position without jamming against the bulkier traditional filters. Finally, I'm just going to talk very briefly about Paul's membrane disc filters for mobile phase filtration. Filtering solutions that are used within high-performance sensitive instrumentation is just as important as filtering samples going into the instrument. The filtration maintains a microbe-free environment within the instrument, prevents clogging of valves and flow paths by insoluble particulates, and keeps baselines consistent and just overall keeps your instrument running smoother for longer periods of time, again, decreasing downtime and decreasing the cost per run. The 3 main types of filters that people generally use for this type of filtration are the water wettable PTFE membrane, which I've talked about quite a bit already. It's a great all-purpose membrane that will be resistant to aggressive solvents, but can also be used with more standard aqueous buffers. Our nylon membrane, or NylaFlow, can be used with both aqueous and solvent-based solutions. Typically, solvents much less harsh than what is used with water wettable PTFE. It has a higher porosity than water wettable PTFE, so it typically will have higher flow rates and higher throughputs. The last membrane I'll talk about is our polyether sulfone or SUPOR membrane. It has an even higher porosity than nylon with a more consistent pore size, again, increasing flow rates and throughput. It is also our lowest binding membrane, so filtering solutions with biological molecules like proteins or nucleic acids are typically done with SUPOR. All these disc membranes can be used with positive pressure or vacuum filtration devices in a variety of different holders and filter funnels. This talk focused on Paul's analytical filtration solutions, with a major focus on filtration of samples for HPLC, UHPLC, mass spec analysis, and other analytical testing procedures, along with mobile phases for HPLC and UHPLC work. We also have filtration options for gases, vacuum pump protection, and pretty much anything else you can think of for analytical lab filtration. Feel free to reach out to us and we can help you with your filtration needs from small to large.
Thanks so much, Craig. I guess everyone's question should perhaps be who wouldn't want to extend column life by 52 times, which reminds me to remind all of you of the option to ask questions at any time for the live Q&A. It's now Brian Rivera's turn on the podium. Brian's going to bring extreme SEC robustness to the table. Brian, the virtual podium is yours.
Thank you for joining today. My name is Brian Rivera, product manager with Phenomenex. Today, we will be discussing size exclusion methods and how to get extreme separations in throughput with a UHPLC column format. To begin, let's talk about the material sciences associated to SEC columns. Size exclusion columns for protein aggregation analysis are primarily fully porous silica. SEC is a non-adsorptive separation, and since silica particles are inherently acidic, they are bonded with a diol stationary phase to minimize electrostatic interactions with basic moieties on proteins. An important point is that SEC separates not by molar mass or molecular weight per se, but by hydrodynamic radius or volume. Although there is a strong correlation to molecular weight and hydrodynamic radius, or RH, as proteins have tertiary and quaternary structures, molecular weight may not be representative of its behavior by size exclusion. So as a review, SEC mechanism is as follows. Analytes are either included or excluded from pores, and this will determine their elution order. So thyroglobulin, which has an RH of 86 angstrom, will elute earlier than IgG, which has a 51 angstrom RH. This is because thyroglobulin will be excluded from the smaller pores, thus earlier retention time or smaller elution volume. Smaller analytes ingress and egress into and out of pores, so they will elute later. RH is important to understand as the behavior of an analyte by size exclusion is fundamentally related to the RH, and even more critical is the pore size. In the pore size distribution, that directly will impact the SEC separation. And so again, pore size is limited to your analyte, and thus pore size critical to column performance for any given application. So let's get that marketing pitch out of the way. Today's presentation will highlight our new SEC column, Biozen DSEC 2. This is a 1.8 and 3 micron particle platform featuring our pore control technology. Today, we will actually focus exclusively on the 1.8 micron for the gains in efficiency one gets with the smaller particle size. Either way, what differentiates this product is a pore volume, remarkably small, 1 mil per gram, whereas other SEC columns typically exceed 1.2 mil per gram, with common ranges between 1.4 to 1.6 mil per gram. And without context, this doesn't seem like much, but the minimized pore size directly impacts column packing bed stability. To fully understand why Phenomenex decided to deviate from the standard practice of high pore volume silica, one needs to understand the fundamental issue with the silica used for size exclusion. And although a mature technique, size exclusion has been plagued with many issues. If you run an SEC method, you've likely experienced all of them. Poor peak recovery due to protein absorption, out-of-the-box failures, unexpected and premature column death, and at the core, the root cause of poor SEC methods are relatively weak particles. SEC particles are overly porous, with pore volumes exceeding 1.4 mil per gram, prioritizing a wider exclusion or separation range. However, a higher exclusion range is only useful for working with an unknown protein, and as such, all that unnecessary pore volume with most SEC methods just leads to a poor mechanical strength silica that cannot be packed at high enough packing pressures. However, even sub-2 micron UHPLC SEC particles, they are a challenge to pack above 10 kpsi in packing pressure, and consequently, we have a loosely packed column bed with a low packed density. A loosely packed SEC column may work great until the rigors of routine testing occur. The column gets fouled or is stored in methanol, and the flow rate is not adjusted to accommodate for the viscosity increase with a protic solvent and aqueous mixture. And the end result is a column void, a huge dead volume at the end of the column bed, and a blob for your chromatography. And no, you cannot restore this column. It must be replaced. And worst of all, some columns are packed better than others, and this is why you've seen that column to column and batch to batch difference. In summary, high pore volume, weak particle, poorly packed column, poor column lifetime. For assessment on packing bed stability, we run a complex sequence highlighted on the right, where we modulate the flow rate using a phosphate buffer with 10% isopropanol. We also include a method shutdown. These conditions put the most stress on the column bed as possible due to the fluctuations in back pressure. We compare against the industry standard hybrid 1.7 micron fully porous silica. This particle is 1.2 mil per gram, one of the smallest pore volumes out there, hence its reputation for being the workhorse for SEC analytical methods. And indeed, the 1.7 micron hybrid silica holds its own 100 hours and only a 24% drop in efficiency for uridine with the 0.35 mil per minute method. However, the changes in back pressure and the column bed stress show erratic behavior, as highlighted by some plates returning significantly less, but eventually restoring back to close to baseline. Data not shown is other silica-based SEC columns typically fail at around 20 to 30 hours or so. Our DSEC2, however, with its low 1 mil per gram pore volume, holds steady for uridine efficiency through those 100 hours with no sign of dropping anytime soon. We attribute this ruggedness to the increased packing density due to the low pore volume silica. Now let's look at some actual chromatography. Here we can see a 150 by 4.6 millimeter ID column packed with the sub-2 micron particles for NIST-MAB. NIST-MAB is a commonly used SEC standard as it has a substantial amount of aggregate within the sample. Monomer and dimers separate out well. Resolution exceeds 1.6, which is a minimum for most SEC methods. And with a 6-minute method, the utility and throughput is quite nice. We'll see in a couple of slides how to improve that, but for now, this is a decent method. However, if you want a higher resolution separation and better fragment separation, you're going to need a longer column. Length is indeed the most important and impactful to a SEC separation. Effectively, the longer column will always win. Here we are looking at cetuximab, which is a good example of fragment 1 and fragment 2 separation, clearly separating out with a well-optimized method. Running the 150 by 4.6 millimeter ID, we can see that the fragment 1 comes off as post-peak and as such does not integrate well. This leads to quite a difference in the percent area reported comparatively to the longer column, where the USP resolution values for fragment for the 300 millimeter length are integrated quite easily using the standard integration parameters. The downside here is that the longer column, of course, double the method length, 6 versus 12 minutes. Fragment and separation is prioritized, however, longer columns are necessary, but implicit with that is a longer method. And so flow rate could be a method development lever to pull to improve separation or even improve throughput, even with the 300 millimeter length. Indeed, given the relative ease of implementation and the potentials for improvements in separation, flow rate probably the most utility in SEC to improve the separation and overall method robustness. Linear velocities required with SEC vary considerably compared to adsorptive separation modalities. That is, large molecules with low diffusion rates require a lower flow rate to allow for the proper ingress and egress into and out of pores. And so we can see with NIST-MAB, when run at 0.2 mil per minute versus 0.35 mil per minute, improvements in resolution of both HMW and LMW are observed. However, it is important to note that the increases in flow rate don't impact the separation too significantly. 0.4 mil per minute still gives a more than acceptable result. This is the benefit of the sub-2 micron format. That is, the experimental space expands quite a bit since the separation at the lower flow rates don't drop off too much. So it would be a matter of prioritizing throughput versus robustness. That said, if throughput is the main intent for the method, whether for screening purposes or overall efficiency in sample processing, cranking the flow rate with the UHPLC format is an option. So here we can see the optimal 0.35 mil per minute flow rate compared to almost 0.6 mil per minute. Notably, there is a drop-off in performance, not necessarily chromatographically, but with the reporting of the high molecular weight aggregate, that is 3.24 versus 2.34 for percent HMW. That's a significant difference in the method result. However, if the intent is just to provide a quantitative, semi-quantitative type of results, the higher throughput method is most certainly an option. And a final example here, looking now at cetuximab and comparing flow rates. Interestingly, the HMW is overreported, with the resolution of lower molecular weight fragment actually improving. This may simply be because smaller fragments are less impacted by flow rates since they have a more favorable diffusion rate. Nevertheless, this will not be quite as a quantitative measure, nor will one expect this methodology to be repeatable. That is, I imagine that the higher flow rate methods, peak areas, and integration might vary more, as the stochastic nature of SEC will be much more pronounced with that higher linear velocity. So implementing a high throughput SEC method, although not quite as quantitative as one might like, may lend to situations that demand for a fast data point, probably more semi-quantitative than other techniques such as light scattering, but either way, a very viable option for improving the lab efficiency and getting that data relatively quickly. If you have any questions, feel free to contact me, Brian R. at phenomenex.com, or you can even text me, 310-561-4882. Would love to engage with you and have further conversations. Thanks once again for listening, and hope you learned something.
Thanks a lot, Brian. I'm sure those analytical scientists working in the extremely tricky field of MAB analysis will be particularly grateful for your presentation. Our third presenter is Jesse Bischoff, who's an R&D scientist at Silcotech Corporation, and I'm personally very keen to see how he plans to open my eyes to the true meaning of high performance. Jesse, over to you.
Thank you very much for that introduction, and thank you everyone for attending this. I'm excited to present essentially where metal ions come from and how it can impact certain separations. My name is Jesse Bischoff from Silcotech Corporation, and hopefully you guys find this information as exciting as I do. So the overview of the talk that I'm going to be given, essentially first off, we're going to look at the impact that metals can have on certain chemical analyses. We're going to look at where metal ions might be coming from, and the spoiler alert here is pretty much everywhere. And then finally look at remedies for preventing metal ion contamination in the HPLC systems. So metals in my flow path, so what? Who cares? Well, many pharmaceuticals are chelating agents, meaning they'll stick to metals in the flow path. Any metal in the flow path could cause peak tailing, could even cause missing peaks. Phosphates, organic acids, oligonucleotides, polar pesticides, and so many more outside of the pharmaceutical industry as well, just cause issues with metals in the flow path. And one other thing to consider with a lot of new chemistries coming out with HPLC columns, metals can have a potential to poison silica beds if they have certain locations where those metals can stick, especially prevalent in mixed mode, helic, and some other new bonding chemistries. The DePra group at Thermo Fisher published a great paper in 2020 looking at these two pharmaceuticals, ciprofloxacin and thiamphenicol. They noticed on two of their instruments, one, they had really good results with both of these compounds. The other, they were seeing a lot of peak tailing and issues with the ciprofloxacin, which does chelate to metal sources. And this was on a biocompatible system that was made mostly of titanium through the flow path. So what they did was they looked, okay, what if we replaced or swap out the two titanium parts to see where this asymmetry is coming from in our peaks. The tubing, nothing really caused an issue there. They swapped out the auto-sampler parts, no issues there either. They swapped out the pump heads, they were starting to see some tailing, and then they swapped out the solvent frits. So things way up from the injection site of where these analytes were coming in to the system, they were still seeing a lot of asymmetry coming from just swapping out the solvent frit. What they found was happening was the titanium from those sources upstream were flowing through their system, hitting the silica bed in the HPLC column and seeing any of these active silanol sites and bonding directly to those silanol sites. So as the titanium is on those silanol sites and that ciprofloxacin came flowing through, that metal chelating area was interacting with the titanium, causing some of the peak tailing to be an issue. They said once the titanium was there, it was really hard, if not impossible, to remove. And one thing that they did mention was this was less of an issue with well-bonded C18 columns, but could still be an issue with if you're looking for like low-level detection. We've done some studies here at Silcotech as well. We looked at this 2-pyridinol 1-oxide. It's essentially the active agent of an antifungal medication, and it's a very powerful metal chelating agent. The chromatograms on the following slide, they're going to show you a significant loss of signal due to the metal interaction between the 2-pyridinol and the metal surfaces. And really what this does is it highlights the interaction that the column wall itself may have with an analyte. A lot of people think you're not having enough flow at the column wall or in metal or any analyte interaction with the metal column wall, but it's not negligible. You can see here, A is an all stainless steel column. C and D, we've flipped out some of the frits on the column with a coated frit or with a titanium frit. Didn't seem to make much difference. The only way that we got this 2-pyridinol 1-oxide to show any usable chromatogram was to eliminate all the metal interaction throughout the column. We coated it with one of our coatings called Dursan, and we'll see how Dursan can help out with eliminating metal interaction a little bit later in this presentation. So looking at the HPLC world, the community itself, pretty much all HPLC componentry is made of stainless steel, unless you go into the bioinert world. Once you go into the bioinert world, the stainless steel causes issues, especially because of the iron, and bioseparations are impacted. So the solutions are really twofold. One, you can either switch that stainless steel out to a new alloy, something like MP35N is becoming very popular, or titanium, or you can move towards polymers like PEEK. Well, if you move towards polymers like PEEK, you're not going to be able to go to as high pressures as you might want to. Not only that, plastic polymers like PEEK are harder to machine to really high tight tolerances like a metal would be able to. And so there are issues with PEEK that are very obvious, but what we wanted to look at was with these bioinert specialty alloys, well, what happens, if you move from one metal to a different metal, are you still going to get metal contamination in your process? And that's what we wanted to really look at and investigate, and that's what the bulk of this talk will be discussing. So when looking at HPLC componentry, we wanted to look at different solvents that you might look at. So water and organic are your two basic solvents you're going to look at. Water for injection, so very, very high purity water is well known to be corrosive towards stainless steel. And there's some literature suggesting that supercritical water, especially with chlorides or phosphates in it, can show corrosion. But there hasn't been a whole lot of work on just stainless steel in HPLC grade DI water and what happens with all these various metals if you're just having it soaking in DI water, what would happen? Or if you have DI water flowing through these components, what would happen? On the organic side, both methanol and acetonitrile are known to impact titanium and stainless steel. I have a couple of notes there. The NASA technical note is on methanol with titanium, and Mowry and others back in 1985 looked at the impact that acetonitrile could have on stainless steel. But very little is known about some of the newer alloys, things like MP35N that a lot of people are using, or another specialty alloy, Hastelloy, that's used a lot in like semiconductor industry for high purity applications. There's very little known about those in organic solvents and what happens. So we decided to take a look at it. We looked at the 4 alloys on the left. All of them were 10 micron frits, except for the MP35N. What we wanted to have was a high surface area so that that solvent can really interact with that material. So we chose frits for that reason. The MP35N wasn't available as Fritz. No one makes it as Fritz to our knowledge. So that is just a rot coupon, just a normal solid coupon instead. And we had 3 different samples. We did just bare as they came. We did clean them with citric acid as well as drying them. And then the other 2 samples are coated with a couple of our coatings. One is Silcolloy. This is a hydrogenated amorphous silicon. And Dursan, which is the coating that we suggest often for HPLC analysis or HPLC needs. It's a hybrid silica material, and both of these coatings are really great because they can fully penetrate any surfaces via the CBD coating process. So quickly, if you're not familiar with the CBD coating process, what we do is we take parts, put them in a vacuum chamber, take all the air out, and introduce our precursor gases into the chamber. Once those are introduced, we heat up the chamber to a high temperature, and anywhere those gases can get, you're going to get coating on the parts inside of the chamber. So the experimental setup, we took the samples, soaked them for a month, and then depending on if they were organic or acid, we would either evaporate off the organic solvent and then redissolve the solids with nitric acid, or if it was just the water, we would take and just correct for the right pH, and then we did analysis via ICP-MS. So getting into the results, stainless steel. So with the 3 just pure solvents here, remember there's nothing added to these, it's just pure DI water, pure methanol, and pure acetonitrile. Our general observations here, the methanol seemed to really attack the stainless steel pretty heavily. And one interesting thing here is that the methanol actually selectively attacked the iron, but it was also the only one that really attacked the chromium at all. The water most likely is repassivating the chromium oxide layer that forms on the surface of the stainless steel, allowing for less of the iron to be released. But you can still see here there was measurable metal ion contamination with both DI water and the acetonitrile. When we looked at our Dursan coated and Silcolloy coated components, they both showed 0 ppb per meter squared of metal ion contamination. So they did a great job of being able to block the metal ions from leaching into the solution here. Titanium was interesting. Methanol was really the only one that was able to leach the titanium ions into solution. There's a lot of literature that explains the passivation of titanium surfaces with DI water as well as with acetonitrile. They're via different mechanisms, but they can both passivate that surface. And so we found this one relatively interesting. Again, both of our coatings showed great baseline levels of metal ion contamination. We did have to adjust our Dursan recipe a little bit due to some of the thermal processes that the titanium saw, but we were able to get it down to 0 as well. MP35N results, this one really shocked us a lot. If you look at just the DI water, water was causing near % levels of ion leaching per meter squared in this result. In fact, to look at the methanol and acetonitrile, we actually had to zoom in to take a look. Here we're looking at tens of thousands of metal ions, ppb per meter squared for these results as well. A cursory literature search doesn't really explain these results all that well. Why does water cause such an issue here? And methanol and acetonitrile really leach quite a bit of metals into solution as well. You're seeing a lot of nickel, a lot of cobalt, very little chromium and molybdenum, comparatively speaking, but a lot of metal ion leaching into solution. We're not really sure why this is happening, but we are going to continue to investigate. The nice part though was both Dursan and Silcolloy again showed baseline levels of metal ion contamination near 0 ppb per meter squared. So we do have a solution to be able to eliminate these metal ions from leaching into solution. And finally, Hastelloy. A lot of people in the HPLC world might not be all that interested in Hastelloy, but we do have a lot of high purity components that are made of Hastelloy. And the nickel-based alloys, as you'd expect, leach a lot of nickel because they're made of mostly nickel. But one thing that was interesting here is the methanol. Again, you can see here, it seems to selectively attack the chromium where acetonitrile and water do not. Again, we don't have a good explanation for why the DI water attacked so aggressively on the Hastelloy, and we're going to continue to look at that. Dursand and Silkaloy, again, both showed baseline levels of metal ion contamination. So feel free to take a screenshot of this, or if you need a copy of this, you can grab this off the web. We have this published on our site, but this is just a summary of the results. We were relatively surprised with how poor MP35 did in these experiments. Hastelloy as well leached a ton of metal ions into solution. Titanium showed good promise if you weren't in pure methanol. So it's something to consider in a lot of these bioinert systems. If you're going to use a titanium flow path, make sure you stick to the DI water or to acetonitrile. Maybe pure methanol isn't a good route to take there. And then finally, any of the coated alloys worked really, really well. Both Dursand and Silkaloy were able to block a lot of this metal ion leaching into solution, which was good to see. So again, looking at solutions, how can you stop metal ions from leaching to the solution? Well, if you're using titanium, avoid methanol or avoid pure methanol. The DePra group from that paper that we discussed earlier, they actually found that if you just add 5% of water to your methanol solution, that was actually sufficient to stop the components from leaching titanium. Now, this is going to be for leaching titanium into solution. This may not allow the complete blockage of your analytes sticking to titanium, let's say frits or tubing or other parts downstream, but it will eliminate some of the titanium from leaching into your solution. Dursand has shown great promise of being able to block metal ion leaching. We've actually had a group that looked at, in the biopharmaceutical world and the oligonucleotide world, they coated a Thermo Fisher DNA Pack PPA 200 column. And here's essentially what they had to say in high salt and high pH conditions. They saw 3 times the recovery of their oligonucleotide of interest. They were able to load up the column much more heavily. They saw at the end of 3 days, they actually had to throw away these columns just because the high salt, high pH conditions would corrode the column to that degree where they weren't getting good separations anymore. They saw 7+ days of use without any iron leaching into solution and impacting their separations. And they saw far less oxidation due to metal ions in solution of their oligonucleotide of interest. So they were really, really happy with the results that they saw there. So we do have future studies to continue to investigate this. So far, we've looked at just pure solvents. What happens if we go a little bit more aggressive? What if we look at TFA or methane sulfonic acid in these solutions? So we currently have that investigation going. We will submit those for ICP-MS here in the very near future, and you can look to our blog. We'll certainly publish those results as we get them. Some robustness studies are planned where we found a competitor's coated hardware actually showed some delamination and flaking issues whenever we unpacked their column and looked at the inside of their column. So how robust is our column after we coat it? And after we pack it and then unpack it and maybe repack it again and unpack it, how robust is our surface? And we have a lot of data to show it's probably pretty robust. And then finally, we are exploring new parts that we can coat. In the HPLC world, people are going smaller and smaller with a lot of componentry, and our current limit for Dursand coating is 0.05-inch ID tubing. We had a project launched in the middle of this year to really push that size down to look, can we get down to the 0.01, 0.005, 0.004 even inch ID tubing so that we can keep up with modern HPLC tubing and get to those smaller dimensions. So if you have any questions, feel free to ask them, or if you want to email me, you can email me. We constantly have application-based studies ongoing to look at, so you can email there as well. And just look for future results at our blog. You can see the site there if you want to go and take a look. So with that, I will turn it back over and thank you for listening.
Thanks, Jesse. A great presentation that raises some extreme questions, perhaps. and I suspect there may be a few from our audience, so a quick reminder to you all to submit questions for the live Q&A at the end. It's now time for our final speaker today. Jennifer Copeland, LC Product Manager at Vici-Valco Instruments, is going to take us on a journey into the extremely small with UHPLC for single-cell analyses. Please take it away, Jennifer.
Hello, and thank you for listening to this talk today. We're going to talk about nanofluidics with chromatographic tools. I'm Dr. Jennifer Copeland. I received my PhD from the University of Nebraska-Lincoln in 2013, working on developing platforms for instrumentation and proteomics. I used mass spectrometry, liquid chromatography, and NMR instrumentation to probe protein-ligand interactions. This experience aids me in my current position at Vici, where I am the LC Product Manager, and I facilitate new product development between our end users and our R&D and engineering teams at Vici. Investigating proteomics on a macro scale provides vital information for systems biology and metabolomics. Microfluidic studies with smaller sample sizes and a lower solvent requirement take advantage of the opportunities provided by high-efficiency columns. The technology of current detectors has improved resolution and allowed us to see variations we couldn't see before. With fused silica capillaries, we can pack columns with increasingly narrow inner diameters and smaller particles. To take advantage of all these chromatographic improvements and investigate samples as small as a few nanograms, we need to think smaller. We use this type of thinking to develop our true nano UHPLC system, where everything is on the smaller scale: pumps, the flow meters, and the valves, and they're all connected with 360 micron tubing. Let's look at the differences between microscale and nanoscale fluidics. Microscale fluidics using 1/16 inch tubing, which is about 1.6 millimeters, keeps the OD and pushes to a smaller inner diameter. Looking at the face of this tubing slice, you can see the scale of the inner versus the outer diameter. This ID has to line up with a bore of the same size in a fitting detail that is bigger than 1/16 inch tubing. Maintaining concentricity is not a trivial task, and small errors of less than 25 micron can lead to dead volume, flow restriction, and carryover. The ID of the 1/16 inch tubing is 150 microns. That's the same size as the first piece of 360 micron capillary tubing. Maintaining concentricity with a smaller fitting detail will be significantly easier using smaller OD tubing where there is physically not enough room for a 25 micrometer error. This means that when we use even smaller inner diameters, going down to 50 micrometers for example, our chances of maintaining concentricity are drastically improved. Let's look at the effect a fitting has on chromatographic peak shape. This experiment is testing different fittings using 360 micron OD tubing. One injection was done on just straight tubing with a 1/16 inch union and adapter ferrules on either side of the 360 micron capillaries. One was done with a pressed quartz fitting, which has a face seal between two pieces of capillary, and the final injection was made on a capillary line using 360 micron union with our 360 micron true nano fittings on either side. The true nano fitting is a very similar peak shape to the straight tubing. The peak is a little bit shallower and there's a very small amount of tailing. The pressed quartz fitting has a smaller peak height, about 50%, and some tailing. And the 1/16 inch fittings have a significant amount of tailing to the point of 75% reduction in peak height. Let's look at using these different size fittings with valves. The valve on the left is our standard Vici Cheminert UHPLC valve with 1/16 inch fittings. Our high pressure Cheminert valves have a stainless steel body, a coated stainless steel stator, and sandwiched between them is the rotor. For a 6-port injection valve, like the one shown here, the rotor has 3 arced troughs connecting the flow paths, and it changes direction depending on position. The circumference around which those troughs meet on a 1/16 inch valve has to be large enough for the fittings and the tubing. However, a true nano 360 micron valve, like the one shown here on the right, has a significantly smaller circumference, which leads to a smaller internal volume. The port-to-port volume is only a few nanoliters, and this size reduction can eradicate dead volume and eliminate cumbersome and expensive adapters. Here is our true nano UHPLC. This operates up to 1500 bar or 22,000 psi and using all 360 micron true nanofittings throughout. It can operate with flow rates as low as 10 nanoliters per minute, which allows for low mobile phase consumption. Each pump has an integrated pressure sensor, and we're working on low volume integrated flow meter as well. Within Vici's long-standing line of Cheminor injection valves, the 360 micron true nano valves have a variety of options and can offer sample injections as small as 5 nanoliters. On the far right, the two tall black structures with the fittings coming out of the top are the two pumps, and this is a binary gradient system. Remember, these pumps have inline pressure sensors, so whether they are dead-ended or in the same flow path, the pressure of pump B follows that of pump A. So as it comes online during the gradient, you do not get a pressure spike. The valve in the middle is the pump valve, and on either side of it are solvent reservoirs. With the low flow rates and minuscule internal instrument volume, you can use as little as a few milliliters of solvent per week. The pump valve is unique, and in one position you can fill the pumps. In another, the pumps are dead-ended so that you can pressure test them. A third position allows you to pump only solvent A through the instrument, and a fourth sends solvent A and B through the instrument. The valve on the left is one of our injection valves, and this one is a top-loading external sample loop injector. When you connect the column to the injector valve and bring this right up to your detector, you can essentially have on-column detection without transfer lines. The low flow rate means no splitting for electrospray emitters. There are a few variations, including different capacity pumps. The pumps shown here are 35 microliters each, and we also have pumps that are 80 microliters each, which operate at a slightly lower pressure. We have options whether you need isocratic, gradient, or continuous flow solvent. Now let's look at the flow path. Remember, the pump valve is unique. In one position, we can fill pump A and B with their respective solvents. Then you turn the pump valve to where pumps A and B are dead-ended and can be tested to hold pressure. Then the valve is turned to allow solvent A to go through the system to equilibrate the column. The injection valve turns to load the sample loop onto the head of the column with more solvent A. Next, we bring pump B in line and take the sample loop out of the line, and gradient can be pumped onto the column and separate the peaks. In order to test the flow rate of our pumps, we used a flame ionization detector and pumped acetonitrile stepwise in 200 nanoliter per minute increments to 1000 nanoliters per minute, and then back down. As indicated in chromatogram A, the pump has a good response. Chromatogram B is where we tested the gradient pumping response. So with water in pump A and acetonitrile in pump B, because this is an FID, a flame detector, then the water will vaporize and the acetonitrile will burn off, creating a signal. This chromatogram follows the programmed method, which was a 5-minute rise from 0% B to 100% B, 1 minute hold, and then drop down to 0% B. In order to test injection reproducibility, we used a pharmaceutical mixture of acetaminophen, caffeine, and noscapine hydrochloride hydrate. Injecting with a flow rate of 2 mL per minute, the detector we used was one of Milton League's group's older single wavelength detectors that has since evolved into their Accent Focus LC, which is an entire unit that you can just bring with you anywhere. It's portable. So we used a short 10 centimeter column with 150 micron ID, and it was packed with 300 micron C18 solid particles. This column was provided to us by Pacific Northwest National Laboratories. Looking at the percent RSD of the retention time and peak area of 5 separate injections, you can see that we have good injection reproducibility. One of our collaborations is with the University of Houston, where we work with Dr. Keen and Dr. Kai. They are studying single-cell bottoms-up proteomics using mass spectrometry and liquid chromatography to investigate cell heterogeneity related to disease. The goals are to exploit the ultra-high sensitivity of the Bruker timsTOF Pro mass spec system with passive technology on single-cell samples and ultra-high performance, low flow, meaning less than 100 nanoliters per minute, liquid chromatography system with sub-50 micron ID columns. So to achieve this, they're going to use our True Nano UHPLC system. For the preliminary work, they purchased a human protein tryptic digest peptide mix from Promega, used a 75 micron ID 25 centimeter column packed with 1.6 micron solid particle C18 that was held at 50 degrees C. Here's their gradient method, where pump A has mostly water with 0.1% formic acid, and pump B has acetonitrile with 0.1% formic acid. They searched the Uniprot Swissprot Homo sapiens database using MS Fragger with a false discovery rate of less than 1%. Here are the preliminary results looking at the number of identified protein groups, using a 90-minute gradient separation at 3 nanoliters per minute on both the True Nano UHPLC and the NanoElute LC. Using both LC systems, the number of common protein groups identified at each sample size, 1, 10, and 100 nanograms, is larger than the protein groups found solely by one system. At the 1 nanogram sample level, the True Nano UHPLC performs significantly better than the other LC system. Another research partner we've been pleased to work with is Peritec. They are manufacturers of compact, multiple wavelength, multi-channel detectors. These are some of their results investigating micro-SEC columns. One of the collaborators probed thermal stresses at varying temperatures on a 50 milligram per milliliter sample of antibody A, using a 7.8 micron ID column running at 25 milliliters per minute flow rate with a 280 nanometer wavelength detector. To scale down to their 1 millimeter ID microbore SEC columns, Peritec used a flow rate of 8 milliliters per minute with an injection volume of 0.4 microliters and their 214 nanometer wavelength detector. The high molecular weight aggregate, dimer peak, that monomer dimer region, the huge monomer peak, and the fractionations can be seen with both standard SEC systems and microbore SEC system. The area percentages are all within 0.2% agreement as well. Another test using micro-SEC columns looks at virus-like particles. Peritec noticed good chromatographic performance and percent aggregation results were consistent with Company 3's results using standard SEC columns. These were monitored at 4 different wavelengths, and the 280 to 255 nanometer peak ratio is consistent with both VLPs having full nucleic acid bonding. This chromatogram shows a reference standard and a bulk drug substance overlapping, and the tests demonstrate the utility of micro-SEC columns with the Vici True Nano UHPLC system and Peritec's ActiPix detector for use with virus-like particles and gene therapy formulations. In summary, because the Vici True Nano UHPLC system exhibits excellent reproducibility and proteomic coverage at low volumes, it is ideal for transitioning to single-cell, bottoms-up protein analyses. The small sample sizes and low flow rates of our UHPLC system facilitate scalability of SEC columns using Peritec's ActiPix detector. Thank you for your time and attention, and please visit our website at www.vici.com.
Thanks so much, Jennifer, for sharing details of the True Nano UHPLC system. Very interesting, I think, given increasing focus on single-cell analyses. Okay, so it's now time for the live Q&A. So everyone out there that's been listening, now's the time to fire over your questions if you haven't already done so. I see we've got some in already. But may I remind everyone, if we don't get through all of your questions live, I'm sure the esteemed panel will come back to you with answers if they're specifically directed to them. So please don't hold back. Okay, so presenters, you're all back there in front of me with the magic of yet more video conference calling. But are you all ready, willing, and able to answer a few questions from our audience?
Sure.
I'm getting nods, and I apologize in advance if I have to remind you to unmute. I seem to have done that many times over the past year or so. Craig, you've been sitting there patiently for a while now, so I think I have a question for you, if you don't mind. Someone says it seems like all you need to do is just choose the water-wettable PTFE syringe filters for everything. I'm not sure that's quite what you said in your presentation, but nevertheless, they say, is there any time you choose a different material?
Yeah, so that's a good question. So yeah, for analytical sample work, it does seem like the easy thing to do is just choose the water-wettable PTFE. It's compatible with pretty much everything that you'll put through. But if you're doing more sensitive work like ion chromatography, where cleanliness of the membrane is important, the ion chromatography or the IC Acrodis filters are a much better choice for that. We actually wash the soup ore to get a couple of the standard ions down to like the low parts per billion. So well below most detection limits on a lot of instruments. And then we have actually a mass spec specific water wettable PTFE membrane that's in a different housing type. It's HDPE instead of the polypropylene. It's much cleaner, a little more expensive, but it gives you a clearer signal when you're doing like MSMS work or have a low abundant molecule. So those would be, for analytical work or sample prep, would be probably my key exceptions.
Thanks so much, Craig. Okay, I've got a specific one here for Jesse. One that intrigues me, actually. I'm not sure what they're hoping to coat with your special coatings, but they say, are there size limitations to what you can and cannot coat beyond narrow bore tubing? Perhaps a small car. I'm not sure how big your chamber is, but if you can shed some light on that, that would be great.
Yeah, sure. So really, our technology is stuff that anyone can do in a lab. Our sort of IP is in doing it at scale. So our largest reactor that we have currently is just over 3 feet or a meter in diameter, and it's about 2 meters tall. So it's somewhere between 6 to 8 feet along those lines. So we have these huge ovens that we can do fairly large parts. As far as small is concerned, like I said in the presentation, we are working now towards getting some of our coatings down to really small diameters, but currently we do coat down to the 0.005 inch ID tubing for some of our other coatings. And we've successfully coated pore sizes down to 0.2 microns on our frits. So, anything from small is great. We can do small parts. Large, if you're looking to coat, maybe like a giant bioreactor,
yeah,
maybe not so much, for that, but certainly anything that, human size, we can coat it.
So we can coat a human. That's good to know. I'm not sure how they would feel after that. Brian, while we're on size, and we're all in awe of your mellifluous, I think is the word, voice and microphone setup. They ask, is the column you shared in your presentation, is it available in larger particle sizes?
Trying to mute here.
I think you were briefly off mute and then you've gone back on mute. Come on, we all need to hear that voice again. While Brian is hang on, here he is. I'm getting a green light.
Yes, no.
There seems to be some cutting in and out going on. Brian, while we try and figure that out, let me move on to a question for Jennifer, perhaps. Someone asks, which I think is fair, what are the customizable aspects of the instrument that you can share with us today?
So for the pumps, you can have an isocratic or a gradient setup if you want. Most of what we've been testing so far is gradient, so we're moving towards getting like a unlimited flow isocratic setup. And for the injection valves, because we make injection valves, we can do practically anything you want. A 10-port injection valve where you can have a pre-column before it. We can do a 6-port standard sample loop injection valve. And if you want really, really small samples, like down to 4 nanoliters, we can do an internal sample injection.
Great. Thank you so much. Where are we? Let me see if I can find another question. Craig, let's come back to you. They simply ask, do you have any suggestions for filtering viscous samples?
Yeah, so the easiest thing is to dilute it if you can, but that's not always possible, especially depending upon the type of work you're doing. So if you can't dilute a viscous sample, then trying to filter, low and slow is a recommendation. I'd use a larger syringe filter too, so something 10 mil or larger definitely helps. Anything smaller than that, you can actually pop the membranes pretty easily with just thumb pressure. So using like a 1 or 3 mil syringe filter, you can get hundreds of psi with just your thumb and burst the membrane and everything comes out. Nothing's filtered, but people seem to be really happy with the throughput. So if you're using a larger syringe filter, just press down until you feel some back pressure and just let it slowly drip out. I mean, you're not going to win any races, but you're also not going to damage anything, and you're going to get it filtered. Sometimes using one of the glass pre-filter syringes can help, but if it's already a clean sample, that's not going to do anything except potentially, add more surface area to bind or potentially absorb your molecule. So, yeah, just low and slow, and just have patience and make sure that you're not accidentally damaging the membrane.
Great, thanks so much, Craig. I think we're still having some technical difficulties with Brian, I'm afraid. So you'll have to wait for that voice to come back. Jesse, are you ready for another question?
Sure.
Fantastic. They ask, how well does the coated column perform when compared with today's standard for metal-free columns, PEEK or PEEK-lined? I know you went into that in a little bit of detail in your presentation, but perhaps you can give us a bit more detail.
Yeah, sure. So, for some of the customers that we've been working with, one in particular was actually that biopharmaceutical customer that I mentioned in the talk. They looked at, on their analytical scale, they were able to get PEEK line columns and everything worked well for them. Once they started going up to prep size, they weren't able to source PEEK lined columns, very well. So we coded some columns for them, and what they said was that the chromatography, other than having to adjust for going up in scale, the chromatography was identical. They didn't see much difference between the two. So they both showed really good inertness. So if you're satisfied with what PEEK might be able to offer as far as columns are concerned, the coating is pretty competitive. It depends on the situation, but yeah, by and large, it's as inert. In some cases, it could be more inert, could be less inert, just depends on the situation.
Great, thanks a lot, Jesse. One here for Jennifer. It seems like a simple question, but let's delve in there. They say, how are columns attached, and what kind of columns can be used with this system?
So because the system is all 360 micron fittings, it is ideal to use a 360 micron column, either self-packed or another one that just has that kind of fitting end. Otherwise, you would need a little fitting, like a union, just to connect to the column. But
Sure.
We don't have any like specific requirements for it. But we also sell fittings.
Sure. And while you're there, they also ask, another person asks, is this compatible with other instrumentation, detectors, autosamplers, etc.? I think you included a couple of examples, so I'm guessing yes. But again, if you'd like to offer a little bit more detail.
Yeah, so like the columns, it can work with practically anything. At the end of the column, you could just bring this instrument up to whatever detector you're using because it is so small. And the software has triggers, so you can see when something's been injected, when the method should be finished, that kind of stuff. So you can start detecting when something is going to be at the end of the column.
Great, thanks so much, Brian. Should we try you again? Perhaps if you turn off your if it's a bandwidth issue, perhaps if you turn off your video, we can at least get the audio feed there. Maybe that's something we can try.
You all hear me now?
I can hear you. Yes. Let's try. Let's go back to the original question. I think it was: is the column available? Is the column available in larger particle sizes?
So the column is definitely available in a larger particle size. The 3 micron, though, can't necessarily be run at the higher flow rates. All of the benefits that we showed with the, um, minimal drop in performance with the higher linear velocities, you just cannot realize that with the larger particle size. That said, 3 micron is probably going to be the preferred particle format, especially in a routine testing environment. Let's say that you are working in a lab that is doing some QC testing and or working with samples which may or may not be filtered, in which case maybe you want to talk to Craig about some filtration. But um, either way, uh, the 3 micron is available. You just can't run it with the so-called extreme conditions there.
Great, thanks so much, Brian. And we can hear you loud and clear, and what a treat.
You don't
While
need to
you're
see
there,
my face. All you need to do is just hear my voice. So
yeah, well, we need one. I think we go with the voice. At least we can hear what you're saying, and that makes a lot of sense. While you're still with us, let me crack on with another question that's popped up. They ask, will the column work for larger analytes, such as IgMs or AAVs? Which I think is a good question.
that's a very good question. Very relevant, especially in the world of gene therapy.
Absolutely.
Being the new hot modality out there. Unfortunately, with this particular column, it was very much a fit for purpose column for monoclonal antibodies in MAB formats, things like ADCs, SCFVs, the IgG1s, those types of things work very, very well in this column, but the pore size distribution was very finely tuned for that particular application. So really anything, larger than, let's say, 8 nanometer in hydrodynamic radius. So this would be an IgM, which can be really anywhere between 12 to 17 nanometer, or AAV, which at least based upon what the literature reports is around 20 or so nanometer. Unfortunately, this would exceed the pore size and the pore size distribution for this particular column. So it's not something to say that we're not working on a larger pore diameter column, but DSEC2, at least as we presented here, definitely would not be applicable to those.
Great, thanks so much for the answer and the honesty there, Brian. We've got one in for another one for Jennifer. They ask, could you please tell me the cycle time or run to run time of your single cell application method with a 90-minute gradient?
So that was what the University of Houston was working on, and they were getting, I think, about 2.5 hours. So running through the column with their cell lysate for about 90 minutes, and then needing to clean off everything and recycle the column.
Great, thank you. One for you, Jesse. I'm not sure where they're going with this question, but they say, are there companies currently offering products with your coatings on them? One would assume so, but go ahead.
Sure, yeah, definitely. We've recently worked a little bit with Thermo Fisher. If you wanted to reach out to me, I could have I have a contact there. It's pretty much custom order at this moment. Also, Microsolve, their diamond hydride columns are available with our coating on. If you go to Microsolve's website, you should be able to find it there. And we're continuously in the pipeline working with other vendors as well. So keep a lookout in the near future.
Great, thanks so much. Another one while you're on there, Jesse. They say in a HPLC column, what portion of the tailing comes from a pore frit, a pore tube, a pore packing material, or indeed a pore connection? Seems like a tricky question to answer, but perhaps you can give us a quick spin.
Yeah. So let's just assume that everything is hooked up the way that it should be. So in that particular case, we did do a study once where we looked essentially, if you're looking at just the column versus the entire system being coated. So with just the column being coated, okay, so let's just say the entire system is coated. If you take away the coating from the entire system and just coat the column, you cut down about half of the peak tailing. So let's assume that you get, maximum non-peak tailing with a completely coated system. Just the column itself is about half of that from what we saw for that particular analyte in that particular setting. So, everything's a little bit different depending on what you're looking at. And then, in the example that we showed there with the really heavily chelating, material, the 2-protanol 1-oxide, the difference between a column being coated versus with the Fritz versus just the Fritz being coated, you can see the dramatic difference there as well. So really it's dependent upon, your system. It depends on, what you're looking at. But what we saw is about half of it's coming from just the column itself. The other half tends to come from the system.
Great, thanks so much, Jesse. Another one's popped in for you, Jennifer. They ask, will the Nano LC have an auto sampler module?
We are working on development of an auto sampler module. It's going to be something relatively simple because these are probably going to be really long runs, so you don't need the throughput. So it would be probably about one plate. We're just trying to integrate that in with our software right now.
Great, thanks so much, Jennifer. I think we've got time for one or two questions. Brian, I hope you're still there. We cannot see your face, but hopefully we can hear you again. Simple one, they ask, what are the back pressure limitations for your column?
Sure. So the back pressure limitations around 500 or so bar, at least for the sub 2 micron particle. That said, to get to that back pressure, one would have to run probably too fast a flow rate, in addition to a really viscous solvent. Something like 10 to 15% isopropanol seems to be a common additive if you're working with antibody drug conjugates. It can certainly get you very close to that 500 bar limitation. But I will say, in size exclusion, the bed collapse that was described in the presentation, that's going to be more an issue with changes in back pressure. So sudden changes, any jolts, right, or the delta pressure is really what's going to cause that column failure. So, even if you are still within the back pressure limitations, if you go from 0 to 400 bar entirely too quickly, that can, lead to some less than ideal column lifetime. So that's always something to keep in mind with back pressure for size exclusion columns.
Thanks so much, Brian. And indeed, thank you to everyone, to Craig, Jennifer, Jesse, and Brian again for your presentations and your input into the Q&A. I'm afraid that's all we've got time for today. Please, though, if you've enjoyed the presentation, do share the link with any colleagues who might benefit from the various examples that we've shared today. Again, a big thanks to our 4 experts and to the companies behind them: Paul, Phenomenex, Silcotech, and Vici Valco Instruments. And finally, I'd just like to thank all of our attendees for watching and sending in your questions. So thank you and goodbye.